This video is about hysteresis. It corresponds to section 16.1 of Applied Analog Electronics. Now, hysteresis is a tool that we use for solving a particular control problem. And this control problem comes up a lot in many different applications. And it's the one of having an on-off control that's controlled by a single continuous input. An example of this is the thermostat that's used for controlling a heater or an air conditioner or a refrigerator, freezer. Almost all those devices have a simple on or off control for whether they're heating for the furnace or cooling for an air conditioner or refrigerator. And the input is a temperature measurement, which is not a simple it's hot or it's cold, it's a continuous value. What is the problem that we address here? Well, let's take a look at a simple solution and see where it runs into trouble. Okay, simple solution. We have got an input and an output for our control device, and the input is going to be something like temperature, and let's say we're doing a freezer or cooler or something like that. So when it's already cold enough, we just leave the thing off. But then when it gets too hot, we want to turn it on. Okay, and so there is a particular voltage here, or temperature, particular input value of whatever the input is, at which we make a transition from off to on. And so that threshold makes this a single threshold system. And it's a very simple system. You just compare what your input is to what your threshold value is to determine whether you turn on or turn off. What's the problem? Well, what happens if the input measurement is noisy? Well, here's an example. The orangish yellow there is an input value with quite a bit of noise on it, and I've put a single threshold here at 1.5 volts. Or 1.48 volts, I guess. And if you look at the output there in blue, it doesn't turn on or off cleanly. As the signal crosses the threshold, the noise makes it cross back. In fact, it may make it cross back several times. And as a result, it flickers on and off at the output. Well, a lot of the devices that we want to control with simple on-off controls are ones that don't tolerate this sort of flickering on and off. You're trying to light a flame, you don't want to say, oh, turn the flame on, turn the flame off, turn the flame on, turn the flame off, because you may not be able to manipulate your valves quickly enough to do that. You may end up with all kinds of damage to things because they're not designed to be moved, to change that often or that frequently. So it's not a desirable solution. If we're just looking at purely electrical stuff, quite often we want to count events. And so here, if we're trying to count, well, how many times did this thing go low? Well, do we really want to count this as 6 or 7? Or did it go low just once here and there was some noise on it? So this is noisy output as a result of noisy input is not really a desirable property. So let's look at a possible solution to that. What we can do is to say, well, if we can remember what state we're in, whether we're on or off, we can say, hey, if we're on, let's require the value to be a little bit lower before we change our mind and turn off again. And if we're off, let's require that it be a little bit higher before we turn on. So we now have two thresholds, a low threshold and a high threshold. And if we're between the two thresholds, then we're just staying in whatever state we're in. We're not changing our mind. And what that means is if we've got some noise, well, once we've crossed this threshold and turned off, we can have quite a bit of noise flickering back and forth here without turning on. We have to get all the way up to here before we turn on, and then once we've turned on, again, we can flicker back and forth here without turning off, as long as our noise is less than this difference between the two inputs. And that's often referred to as the hysteresis value, or if it's a voltage, the hysteresis voltage. And that's the difference between these two things. So as long as your noise is less than that, you're not going to get sort of the double transitions. You'll only get transitions when you actually move all the way past one of these. Let's take a look at what that looks like with the same noisy signal we looked at before. Okay, so this is the same noisy signal, but now I've got two thresholds, at 1.1 volts and 1.9 volts. And you can see that the blue signal is not making multiple transitions. Because I had the sort of smooth curves like I drew in the on the paper, there's a little bit of a glitch, just a small one, at the transitions. And that was easily removed by just running the thing through ordinary digital logic. Digital logic would not see that tiny glitch as being a change in value. It's just a 1 until you get all the way down to the 0, and then it just stays 0 all the way until you make the transition up to the 1. So those tiny glitches are easy to clean up and basically don't affect anything. So here we've got something that makes just a single transition down to low, single transition up to high. If we were counting how often we were low, we would just see this as a single event. If you were doing something where we were turning motor, or refrigerator or heater on or off, we'd only have a single, hey, we've got to turn it off for a bit, and now we turn it back on again. Everything is working the way we would want it to, as long as the noise is less than that difference between the two thresholds. Once your noise gets bigger than that difference between two thresholds, then you can get the flickering back and forth again. Okay, so what else do we care about on this? Well, one thing is when we're doing this, we really don't want that sort of smooth curve that I drew here. It'd be nice to have a very sharp transition where it just goes, hey, I go almost no voltage change at the input to go from 0 to 1 on the output. And that's done by using digital logic. In fact, the circuits we usually use for doing these things are called Schmitt triggers. And a Schmitt trigger is got a nice digital output, and it makes a very fast, very sharp transition. So it's used very frequently for cleaning up signals to turn them into digital signals. It's even used for cleaning up digital signals that come in, because if noise gets added to a digital signal, you still want to have a clean interpretation of it as a 0 or 1. So essentially all the digital inputs on things like the TCLC microcontroller board, they all have Schmitt triggers on the inputs just so that it interprets whatever's coming in as a clean digital signal. There's also another thing that I should tell you about, and that is that there's a slight variant on what I've been showing you for hysteresis. Everything I've been showing you so far had low input produces low output, high input produces high output. But you can turn that around the other way. You can have something that has a high output for a low input and a low output for a high input, and the hysteresis can still be done. And this is an inverting Schmitt trigger, or as it's sometimes written, a Schmitt trigger inverter. And we'll be using one of these, the 74HC14N is a Schmitt trigger inverter. And that's probably about all you really need to know about for hysteresis right now. In a subsequent video, we'll look at some circuits that use hysteresis in some somewhat surprising ways.